Okay, so this is video lecture 18, and in this video lecture we are going to unpack the elements of factorial designs. So before we get into the specifics of factorial designs, it is necessary for us to take some time and unpack the terminology that we will be using going forward to describe factorial designs. And so, as you know from your reading in Chapter 8, factorial designs are designs in which there is more than one independent variable. That is, there are two or more independent variables that we are manipulating and or working with. Contrast that with single factor designs in which there's a single independent variable. So because we are talking about two or more independent variables, it becomes necessary to be clear in terms of the terminology that we use to describe these factorial designs. And so I want to direct your attention to this terminology here at the top of the screen, A by B or A by B by C terminology when describing a two independent variable factorial design versus a three independent variable factorial design. And so from your reading in Chapter 8, you learned that the way that researchers describe factorial designs, if it's a two-factor design, that is that there are two independent variables. You describe them as A by B. So, for example, imagine that you had an experiment that was described as a 2 by 4 factorial design. Now, you might be compelled to look at that and say, "Oh, that makes sense. It's a factorial design that has two independent variables, each with 4 levels." That actually is incorrect. When you look at this 2 by 4, you should interpret this as a factorial design that has two independent variables, independent variable 1, independent variable 2. The first independent variable has 2 levels. The second independent variable has 4 levels. 2 by 4. First one has 2 levels. The second one has 4 levels. Another example would be a 3 by 2 factorial design. That is a factorial design that has two independent variables. The first one has 3 levels. The second independent variable has 2 levels. Similarly, if you are describing an experiment that has 3 independent variables, you use the A by B by C terminology or nomenclature. So, for example, a 2 by 2 by 4 factorial design is one in which there are 3 independent variables. The first one has 2 levels, the second one has 2 levels, and the third one has 4 levels. Another example would be a 3 by 3 by 2 factorial design. Again, that is an experiment that has 3 independent variables. The first one has 3 levels, the second independent variable has 3 levels, and the last independent variable in that example has 2 levels. So get comfortable with this terminology. Quickly ascertain that a 3 by 4 factorial design is one that has 2 independent variables, one with 3 levels and the other one has 4 levels. A 3 by 3 by 4 factorial design is a factorial design that has 3 independent variables. The first independent variable has 3 levels, the second one has 3 levels, and the third one has 4. And the sooner that you get comfortable with that terminology, the easier it will be when things get more complicated, when we start unpacking the different types of factorial design. Since you've now read Chapter 8, you understand that there's a decision tree that goes along with determining the type of factorial design. And you now know that there are 7 of them, and it can get complicated when you're trying to understand the nature of each of the independent variables that you're discussing. So now that we have the terminology, have discussed the terminology, I want to make a distinction between number of levels and number of conditions. Number of levels is a concept that we've been discussing now for several chapters, and everyone understands what number of levels means, or what levels means. It means the number of situations, or the number of differences, or the number of manipulations that are occurring in any one independent variable. A single factor experiment, for example, that has 3 levels, a control group, a low dose, and a high dose, right? There's 3 levels, there's 3 conditions for that particular single factor experiment. So levels, when you use the term levels, you are applying it to a single independent variable. I bring this up because the term levels and conditions is used synonymously in single factor designs. A single factor experiment that has 3 levels is also a single factor experiment that has 3 conditions. For example, an independent group's single factor design that has 3 levels to the independent variable, a control group, a low dose, and a high dose, just so happens it also has 3 separate conditions, or 3 separate groups. One group gets no drug, one group gets a low dose, and one group gets a high dose. So conditions and levels, those terms can be used synonymously in single factor designs. That is not the case in factorial designs. Levels, again, refers to a single independent variable. Conditions in factorial designs refers to the total number of conditions across the entirety of the experiment. So for example, going back to this original 2x4 factorial design here, again, it's an experiment that has 2 independent variables. The first independent variable has 2 levels. The second independent variable has 4 levels. So within each of these independent variables, we talk about levels. 2 levels here, 4 levels here. But collectively, across the entire experiment, this 2x4 factorial design experiment creates 8 separate conditions. So be clear about this fact that conditions and levels mean different things when we're talking about factorial designs. Levels refers to any one particular independent variable. Conditions refers to the entire experiment in total. So at the bottom of the screen, I want to discuss an effective way to depict factorial designs. And so because we're talking about multiple independent variables, it can get complicated. And so one effective way to present, visually anyway, factorial designs is to use what are called factorial matrices, or a factorial matrix. So in the bottom portion of the screen there, I have a factorial matrix that describes an experiment that is examining the effects of sex, which is factor A, or independent variable A, and crowding, which is factor B, or independent variable B, on memory. Memory, of course, is our measure, or our dependent variable. So that factorial matrix then visually depicts the outcome, or visually depicts rather the design of our fictitious experiment designed to examine the effect of sex of the subject and crowding on memory. So you might be interested as a researcher, what effect does crowding in schools have on students' ability to remember? You also might be interested to assess whether males and females respond differently to different crowding situations. So now you've got 2 factors of interest in that hypothetical experiment: the effect of crowding on memory and the effect of sex on memory. Those are your 2 factors of interest. Again, that's what independent variables are. These are the things that drive our interests. So factor A in this hypothetical study is sex, males versus females. It has 2 levels. Factor B is crowding, low, medium, or high. It has 3 levels. Taken collectively, however, this 2x3 factorial design creates 6 separate conditions, and that is depicted visually there in that factorial matrix. So within that factorial matrix, there's a terminology that I want you to be familiar with. It kind of harkens back to an earlier day when analysis of experimental data was a little bit more difficult, and so we had to categorize or label our data points in such a way so that the analytical programs that we used to analyze the data could identify which group a particular participant belonged to. So note that we have 2 factors, factor A and factor B. Factor A is sex, factor B is crowding. There are 2 levels to factor A and 3 levels to factor B. Collectively, it creates a 2x3 factorial matrix and 6 separate conditions. And so level 1 and level 2 of factor A, level 1 is males and level 2 is females. Level 1 of factor B is low crowding, level 2 of factor B is medium crowding, and level 3 of factor B is high crowding. We can take that information and identify quickly and put participants into particular groups or conditions based upon our understanding of what level they are for each of these factors. And so, for example, a male that is randomly assigned to the high crowding condition falls in the cell of that matrix of A1, B3, right here. So males, level 1, high crowding, level 3. That is cell A1, B3. And you can use that as a way to describe a particular participant and what condition they fall in an experiment. If I asked you what are the characteristics of participants that fall in cell A2, B2, well, you could quickly look at this factorial matrix and ascertain that cell A2, B2 represents females in the medium crowding condition. And so this is this is a nomenclature or terminology that one can use to identify participants and identify conditions within a factorial design. And I will want students to be familiar with this labeling system. So we now need to make a further distinction in factorial designs. So when we discussed single factor designs and we talked about whether an effect of an independent variable was significant or not, we didn't need to make a distinction between that effect and anything else, because there is only one effect. There's only one independent variable. So the term main effect never came up in Chapter 7. A main effect, by definition, is a significant effect between the levels of a single independent variable. For single factor designs, there is only one independent variable. There is either a significant effect or there isn't. So there's no need to make that distinction of main effects in single factor designs. There's only one independent variable, so that there's only one possible effect. Now, of course, that effect can occur across the levels of that independent variable, whether it's 2 levels, 3 levels, 5 levels, and so forth. But the effect refers to an effect of a single independent variable. We need to make a distinction or use the term main effect in factorial designs because there is more than one independent variable. And so there might be a situation in which you have 3 independent variables in a factorial design, but only one of them proves to create a significant difference among the levels of that independent variable. The other 2 are non-significant or benign. There are, in that case, with 3 independent variables, there's a possibility for 3 main effects. So that's why a distinction must be made. That's why we need to use the term main effects now when we weren't using it in Chapter 7. Main effects refers to a significant effect between the levels of any one independent variable. And so because we're talking about 2 or more independent variables in factorial designs, we need to make a distinction, because it's possible that depending on how many factors you have in your study, you may have significant effects among all of those factors, or among some of those factors, or among none of those factors. So that's a distinction that needs to be made. So I have that 2x3 factorial matrix from the previous slide. Factor A is sex with 2 levels. Factor B is crowding with 3 levels. And this hypothetical study is studying memory ability. Does crowding and sex of subject have an effect on memory ability? So it's a 2x3 factorial design. I have now populated that 2x3 factorial matrix with some fictitious data. And so we'll say that each one of those cells represents an average of 10 participants. That there are 10 males in the low crowding condition, 10 different males in the medium crowding condition, and 10 different males in the high crowding condition. Similarly, there are 10 females in the low crowding condition, 10 different females in the medium, and 10 different females in the high crowding condition. Going back to that terminology, if I were to ask you what is the value in cell A2B1, your answer would be 13.5. So the average in cell A2B1, again, level 2 for factor A, which is females, level 1 for factor B, which is low, and so here we have the mean for that particular cell, the mean for those 10 females that were tested in low condition. In this case, it's 13.5. So looking at this 2x3 matrix, I've populated it with cell means. I've also calculated what are called marginal means over here, and so we have 18 over here for males, 18 for females, and then I have 13.75, 18.25, and 22 for low, medium, and high. These marginal means represent the main effects of the two, or possible main effects rather, of the two independent variables in this hypothetical study. The marginal means are calculated by averaging across the levels of the other independent variable or variables. So we have two independent variables. The first one is sex, the second one is crowding. There are two independent variables, therefore there are two possible main effects in this study. The number of main effects is equal to the number of independent variables. If you have three independent variables, there is a possibility for three main effects. Four independent variables, four main effects, and so on. So we have two independent variables, sex and crowding, and therefore we have the possibility that of two main effects occurring in our study. And so I've calculated and examined the main effects for this particular study by calculating marginal means. What does that mean? It simply means that I've averaged across the levels of the other independent variable. So let's isolate sex. There are two levels, males and females. Is there an effect of male or female on memory in this study? Well, how do I calculate that? Well, males, there are 30 males in this particular study, 10 in the low crowding condition, 10 in the medium, and 10 in the high. I average across all three of those conditions there. I ignore the levels of the other independent variable. It is not of interest at this point to calculate the main effect I want to see. Is there an effect of being either male or female on memory in this study? So I ignore or collapse across the levels of the other independent variables. So 14 plus 18 plus 22 divided by 3 gives me a mean for the males of 18. Same thing for the females. I average across the levels of the other independent variable, crowding. I average across these three levels here, 13.5 plus 18.5 plus 22, divide by 3, and lo and behold, the average for the females is 18. 18 is equal to 18. Obviously, in this hypothetical study, there is no significant difference between males and females in terms of overall memory ability. So there's no main effect of sex in this study. What about crowding? So we've got a second independent variable. Let's examine the effect of crowding. This has three levels, low, medium, and high. And so I do the same thing. I collapse across or average across the other independent variable being sex, and I calculate marginal means for low. 14 plus 13.5, add those up, divide by 2, the average is 13.75. The average across the two levels of medium crowding is 18.25, and the average at high is 22. Now, looking across these three levels of 13.75, 18.25, and 22, there does seem to be a difference as we go from low to medium to high crowding on memory ability. If you were to subject this data to inferential analysis, you would discover that this is a significant difference. And so as you go across the levels of this independent variable, there does seem to be a main effect operating here. And so, in this example, in this hypothetical experiment that we have designed here, 2x3 factorial design, there is no main effect of sex, but there does appear to be a main effect of crowding. Again, a main effect is a significant effect between the levels of a single independent variable. Crowding seems to have an effect on memory. Sex does not. So continuing on with our discussion of main effects, and I'm a big fan of graphs. Having just defined what a main effect is, I've got two graphs on the screen here that depict the outcome of that hypothetical experiment of crowding and sex on memory. Which graph, A or B, plots the main effect of crowding? So figure A actually plots males and females separately as they go from low to medium to high crowding, whereas in graph B, we have an average across the male and females in each of the crowding groups of low, medium, and high. Based upon our definition of what a main effect is, which of these graphs satisfies that definition? Based on our definition, only graph B does, because a main effect is a significant effect of one independent variable. You collapse across the levels of the other independent variable. You collapse across sex in this case, and so the average of these 2 points is this, the average of these 2 points is this, and the average of these 2 points is this. And so the answer to the question, which graph plots the main effect of crowding? It is graph B. So let's unpack some actual experimental examples that demonstrate the effect of, or rather that demonstrate main effects. So there's a classic study that you're probably familiar with. I suspect that most introductory psychology textbooks still include this classic study when discussing the factors that affect memory. It's the Wallen-Weber and Lowry study from 1972, in which they studied the effects of combined imagery, that's factor A, with distinctiveness of the image, that's factor B, on memory, and that is the dependent variable. And so this was designed as a 2x2 independent groups factorial design. And so 2 levels to each factor, 2 levels to the image factor, whether it was combined or separate, and 2 levels to the distinctiveness factor, either bizarre or normal. So I direct your attention to the lower right-hand corner of the screen here. Here are some images from the Wallen-Weber and Lowry study here. When I discuss the image factor being combined or separate, we can see here that these are, up here in the upper left-hand corner, that these are separate. We've got a cigar and we've got a piano. They are not combined. They are separate. We've got the piano here and the cigar here. Whereas in the bottom left-hand corner, they are combined. The piano and cigar are combined into a single unitary image. Furthermore, you can manipulate the distinctiveness of the image. And so it could be normal, in which a piano is resting on the ground, and a cigar which is lit on one end. That's normal. That's how you typically light a cigar, and that's typically how pianos are. They are resting on the ground. You could make it distinctive and bizarre by having it float off into space with the keys coming off of it. That is quite unusual, quite bizarre. Furthermore, cigars that are lit at both ends are unusual or bizarre as well. And so here's a situation in which they are not interacting. You have the piano here, you have the cigar here, and so they are separate but bizarre. And down here it is interacting. They are together. You have the cigar resting on the piano keys, but actually underneath the piano keys, and so that's bizarre. But they are interacting, or they are combined into the same image. And so that creates a 2x2 factorial matrix. Image element being factor A, the distinctiveness element being factor B. I've populated that 2x2 factorial matrix with data from the actual study. The participants that saw the combined and bizarre image, the average across all of those participants was 6.67. For the combined and normal condition, it was 6.6. For the separate but bizarre image, it was 3.05. And for the separate but normal image, it was 3.5. Now, once again, before we go further, if I were to ask you what is the cell mean for in cell A1B2, you would quickly look at that factorial matrix and surmise that the cell mean for cell A1B2 is 6.6. A1 is combined, so factor A, level 1, level 2. So level 1 for factor A is combined, level 2 for factor B is normal. The mean for this cell, or cell A1B2, is 6.6. I've also calculated marginal means. 6.64 is 6.67 plus 6.6 divided by 2, and so here's the marginal mean for the combined group, the marginal mean for the separate image factor, and then furthermore, I've also calculated marginal means for the distinctiveness factor. Bizarre, the average of these two is 4.86. The average for these two is 5.05. And so the question then is, are there any main effects from this particular study? Well, focusing only first on the factor A, the image factor, is there any difference between combined and separate images? Well, you can clearly see that 6.64 is different from 3.28, and Wallen, Weber, and Lowry determined that this was a significant difference, that there was a main effect of whether the images were combined or separate on the participants' ability to remember the elements of that image. And so when things were put together, they remembered more of it than if they were separated apart. So there's a main effect of the image factor. Now, focusing then only on the distinctiveness factor, the main effect of distinctiveness, 4.86 and 5.05. These numbers are certainly not the same, but as it turned out, Wallen, Weber, and Lowry found that that was a non-significant difference, that 4.86 and 5.05 are sufficiently similar for them to conclude that there was not a significant main effect of distinctiveness. So for this study, there was a main effect of the image factor, but not a main effect of the distinctiveness factor. Now let me say something before going on. On an exam, if I want you to detect, by looking at a factorial matrix, if I want you to be able to conclude that a main effect exists, I will make sure that the differences are sufficiently large that you would conclude that there does seem to be a difference between the levels of that independent variable, i.e. that there is a main effect of that factor. I won't try to be sneaky. I won't try to make them subtle. If it appears to be small, as is the case here, 4.86 and 5.05, they're not the same, but I think everyone would agree that they're not sufficiently different for anyone to conclude that there's a main effect of the distinctiveness factor. So, one main effect in this study, two independent variables, two factors, but only one of them turned out to have a significant effect on memory, and that was the image factor. Continuing on with our discussion of main effects, and this comes right from the textbook, an interesting study to say the least by Gladue and Delaney from 1990, in which they measured attractiveness rating, and that was the dependent variable, for men and women, that's factor A, the sex of the rater, in bars at different times during the night. And so the different times during the night while at a bar was factor B. So two different factors, the sex of the rater and the time at which the ratings took place are the two factors, sex being factor A, time during the night being factor B. And so I've created a 2x3 factorial matrix here. We've got two levels to factor A, the sex of the rater, men or women, and then factor B is time during the night. There was 3 times that they assessed the attractiveness, at 9 p.m., 10:30 p.m., and at midnight. So a 2x3 factorial matrix. I've also populated it with the data from the chapter and have calculated marginal means for both the factor A, sex of the rater, and factor B, the time at which the ratings took place. And so looking just at the tabular data here, we can see that there seems to be a difference between men and women, isolating factor A only, the sex of the person making the rating. there seems to be a difference between men and women, 6.2 versus 5.2, that men typically rate women higher than women rate men. And although this difference seems to be subtle, it was determined to be significantly different, that men seem to rate women significantly more attractive than women rated men. The second factor being time, 9 p.m. versus 10:30 versus midnight. The marginal means when you average across the sex of the rater, 5.2 at 9 p.m., 5.8 at 10:30 p.m., and 6.1 at midnight. They also concluded that there was a main effect of time, that as time progressed in the bar, both men and women consistently rated members of the opposite sex more highly. And so as the night progressed, members of one sex found the other sex more attractive, regardless of whether they were men or women. And we can see that visually here in the graph here. The white bars are men rating women, the blue bars are women rating men, and we can see if we average across, and so keep in mind that these marginal means represent a main effect of sex, factor A. The average of this, and this, it's 6.2 for the men, and the average of this, and this is 5.2 for the women, a main effect of sex. And then if we ignore sex and look at time, 9 p.m., 10:30, and midnight, we average these two bars, and the average is 5.2. We ignore sex, we average these two bars, it's 5.8, and if we average these two bars, it's 6.1. And so as we go from 9 to 10:30 to 12, it gets significantly higher. Two main effects in this particular 2x3 factorial study. Again, a main effect is an effect of any one independent variable in your study. And so the number of main effects that are possible is equivalent to the number of independent variables that are in your study. So now that we've discussed main effects, let's unpack the other possible outcome in factorial designs, and that outcome is an interaction or interactions. And so what is an interaction? By definition, an interaction is an effect of one is when the effect of one independent variable depends on the level of the other independent variable or variables. I will repeat that. An interaction is a situation in which the effect of one independent variable depends on the level of another independent variable or variables. And so, based upon that definition, one may ask the question, are interactions possible with single factor experiments? Well, again, let's go back to the definition. An interaction is a situation in which the effect of one independent variable depends on the level of another independent variable or variables. And so based on that definition, the answer to that question is no. Interactions are not possible with single factor experiments. For an interaction to occur, it has to occur between two or more independent variables. And so let's provide an example to a more concrete example rather to unpack what we mean when we discuss interactions. So imagine an experiment, a 2x2 factorial design that examines the effect of stress, and so that's one independent variable, factor A, and an anti-anxiety drug, that's factor B, on attention. And so in this example, attention is our dependent variable. So two factors. Factor A is the amount of stress that the participants are subjected to, and factor B is some new anti-anxiety drug. Two levels, either they get it or they don't, control and experimental, on attentional score. So imagine you work for a drug company, they've got this new anti-anxiety drug, and they want to make sure that this anti-anxiety drug doesn't differentially affect or doesn't affect attention, because if it does, they may have a marketing problem and so forth. So you were asked to conduct a pilot study and see, does this anti-anxiety drug affect attention? And specifically, does it affect attention under different levels of stress? So you conduct the study as a 2x2 factorial design. You simply have low stress versus high stress. You have them do a simple task versus a difficult task, and then either the presence or absence of the drug. And that, of course, produces a 2x2 factorial design. And so I have then populated a 2x2 factorial matrix with some hypothetical data from this particular experiment. Imagine that the cell means for this particular experiment is 71, 66, 51, and 60, meaning that in cell A1B1, that individuals in the low stress condition that were not given the drug, the average of this group is 71. The average of this group that was subjected to low stress but received the drug was 66. This group, the mean of the individuals that were subjected to high stress but did not get the drug was 51, and individuals that were subjected to high stress but did get the drug is 60. Again, if I were to ask you the question, what is the value in cell A2B2, you would quickly look at that 2x2 factorial matrix and know that in cell A2B2, the value is 60. I've also calculated marginal means so that we can isolate any possible main effects of stress or drug in this particular 2x2 factorial design. The marginal means for stress, so the main effect of stress, the means are 68.5 for the low stress condition. So we collapse across the drug, collapse across or average across these two values, it's 68.5. We average across these two values, it's 55.5. And then we isolate drug to examine any main effect of drug. So we average across these two values and it's 61, and we average across these two values and it's 63. So the no drug average was 61, the drug average was 63. The low stress average was 68.5, the high stress average was 55. So now we have information to draw conclusions about possible main effects and or interactions that operate in this hypothetical study. Well, looking at this, we can see, I think, quite clearly that if we look at the stress factor, factor A, and look between the low and high conditions, we can see that those numbers are sufficiently different that we would conclude that 68.5 is significantly higher than 55.5. That being subjected to stress is in and of itself enough to alter attention scores on the particular measure. Isolating the drug effect, main effect here, 61 versus 63, these numbers are not sufficiently different for us to conclude that there would be a main effect in this hypothetical study between the presence or absence of this new anti-anxiety drug on attention. So in this example here, we have evidence of one main effect, a main effect of stress, but no main effect of drug. The question is that all that is occurring? And the answer to that question is no. There actually is an interaction going on in this experiment. And to isolate that interaction, to make it more obvious, I've created a graph that depicts this table data here as graphical data here. So here we have our level of factor A here, low stress versus high stress, and then in the XY space here of the graph, I have two lines representing the two levels of factor B. No drug, which is level 1, and drug, which is level 2. And so look at that figure. You can see that those lines actually cross. And so I'll give you a little bit of a hint here that anytime you see graphs in which lines that either converge, diverge, or cross, that's pretty compelling evidence that there's probably an interaction going on somewhere in that data set. And that would be the case here. And so see what's happening here in this graph. At low stress, depending on whether you got the drug or not and its effect on attention score, that if you were given the drug and subjected to low amounts of stress compared to the group that didn't get the drug, your attention score, or that person's attention score, is lower than the person that didn't get the drug. So at low stress, the presence of the drug actually seems to impair attention. But at high stress, that effect reverses. At high stress, the presence of the drug seems to facilitate attention relative to the no drug condition. Now recall, we determined that there was no main effect of drug. If you only looked at the main effects for this study, you would conclude that this new anti-anxiety drug did not have a significant impact or a significant effect on attention. But that's only part of the story. Actually, the effect of the drug depends on the level of stress. At low stress, the presence of the drug actually impairs attention. The drug group did worse than the no drug group. But at high stress, that effect is reversed. The drug group did better, was facilitated relative to the no drug group. And so this is a classic example of an interaction. There is no, in this hypothetical study, the main effect of drug was insignificant. There is no difference between drug or no drug in terms of attention. However, if we look at the effect of drug as a function of stress, or the effect of drug depending on the level of stress, we see that the effect of the drug depends on the level of the stress. When stress is low, the drug seems to impair attention. When stress is high, drug seems to facilitate attention. That is the definition of an interaction. So before I move on from this slide, one last question about interactions and their importance relative to main effects. Are interactions more important than main effects? The term important is somewhat of an incorrect term there, but they are more interesting to say the least. Oftentimes when you read articles that are discussing both main effects and interactions, the interactions are described before the main effects because they're a little bit more complex and they actually speak to a more interesting, in many cases anyway, a more interesting effect that's operating. That the effect of one independent variable depends somehow on the level of another independent variable, certainly in the data that's depicted here on the screen. That's a fascinating effect. If you work for this drug company and you actually see a reversal of the effect, that under one condition the effect of the drug is one way, but under a different condition the effect of the drug actually reverses, that's an important outcome to know. And again, it is a classic example of an interaction. The effect of drug, in this example, depended on the level of stress. If we didn't have stress, if stress was not a factor in this study, if they only assessed drug, presence or absence of the drug on attention, the conclusion would be that the drug has no effect. 61 versus 63. There is no effect of drug on attention. However, when we add that second factor, in this case stress, we actually unearth some interesting outcomes. And that the effect of that drug overall seems to be benign, but when you subject participants to stressful versus non-stressful environments, it seems to reveal an effect of that drug that was not apparent based upon the effects of the drug alone. That's why interactions are so important. So now that we have discussed the distinction between main effects and interactions, I want students who take my class to be able to look at graphical data. Again, I find graphs to be important, and being able to ascertain what is being depicted in a graph as being an important skill that students should learn and be adept at. I would like to go through the 8 possible outcomes in a 2x2 factorial design. These 8 possible outcomes are depicted in the PDF version of this video lecture. So you have this in front of you, but I just want to highlight the procedures that one would use to ascertain whether main effects and or interactions are occurring in graphical data. And so I'm going to keep it simple, but I want students to be able to just look at a graph and say, aha, I see it. There's a main effect of this factor, but not a main effect of that factor, and there appears to be, for example, an interaction. That's an important skill to have. Again, a graph says 1,000 words. And if you can look at a graph and not only ascertain what the independent variables and dependent variable is or are, but understand the nature of the effects that are unfolding in that graph, that is a very important skill to have. And so I want to foster that skill in this portion of the video lecture. So the basic 2x2 design can have 8 possible outcomes. And so 4 of those are depicted on this screen. You can have a main effect for factor A. You can have a main effect for factor B. You can have main effects for both factor A and factor B. Or you can have a main effect for factor A plus an interaction. Those 4 outcomes are depicted graphically at the bottom of the screen. And so I want to show you ways in which you can look at these graphs and quickly ascertain, aha, I get it, factor A, there's a main effect, factor B, not so much, and so forth, so that you can look at these graphs and draw conclusions not only about what's being tested and what's being measured, but what effects are occurring and whether interactions exist. So main effect for factor A is being depicted here. Main effect for factor B is being depicted here. Main effects for A and B depicted here. And then number 4, main effect for A plus interaction is being depicted here. So main effect for factor A. And all of these graphs, factor A is depicted on the x-axis. Factor B is being depicted as the 2 lines in XY space. So using the same example from the previous slide, the effect of stress and drug on attention, let's examine this particular graph here and understand why this graph, this outcome, depicts a main effect for factor A only and not for factor B. Again, factor A is on the x-axis, factor B is depicted in XY space as separate lines. So factor A, level 1 and level 2. Factor B, drug versus no drug. Factor A at low, how do we do this? Well, how do you calculate main effects? You average across the levels of the other independent variable. Well, the other independent variable is being depicted here as 2 lines. And so level 1, low, average across the no drug and the drug condition. Well, these points are essentially right on top of each other. The average at low is 50. The average at high is about 70. 50 is certainly different from 70. So we have a main effect of factor A. We have a main effect of stress. Low is significantly different from high, but we don't have a main effect of factor B. How do you do that? We collapse across the levels of the other independent variable. So factor B is represented as this line versus that line, level 1 and level 2. Level 1, level 2 for factor A, so we average across the other levels of the other independent variable. And so this line here represents the no drug condition. And so what's the average at high and low for the no drug condition? Well, the average of 50 and 70 is 60. For the drug condition, the average of 50 and 70 is 60. The average of these 2 lines across the low and high stress condition is the same, in both cases 60. So we have a main effect of factor A. This average is different from this average, but we don't have a main effect of factor B. This average is no different from that average. For the second graph here, we have a main effect for factor B, but no main effect for factor A. So let's isolate factor A first, low stress versus high stress, and average across the level of factor B. No drug versus drug. What is the average of these 2 points? Well, the average of these 2 points is 60. So at low stress, the average is 60. At high stress, the average of these 2 points is 60. There is no main effect of stress. What about drug versus no drug? Well, what's the average across the low and high stress conditions for the drug condition? Well, the average of 72 here and the average of 72 here. The average is 72 for the drug condition. For the no drug condition, the average is 52 at low and 52 at high. The average is 52. 72 versus 52, these are different. We have a main effect of factor B, no main effect of factor A. Graph 3 shows main effects for factor A and factor B. Well, let's isolate factor A, which is low versus high stress. What's the average at low? Well, the average of these 2 points is somewhere around, we'll say 49 or 50. We average across the level of factor B, which is drug. So this is, on average, we'll say it's 50, and the average across these 2 points is around 70. So the difference between the average at low and high is 50 versus 70. That's a main effect of factor A. What about main effects for factor B? Well, here we have the drug condition. What's the average across the low and high stress conditions? Well, the average at 50 and 70 is 60. And for the no drug condition, it's 45 to 65, or about 55. So we have 65 versus 55. There seems to be a difference between these two. So main effect for factor B, main effect for factor A. But these two lines are parallel. There does not appear to be an interaction. Recall on the previous slide that I indicated that evidence for interactions is often indicated by lines that converge, diverge, or are crossing. These lines are parallel. There is no main effect. There is no interaction operating in this particular graph. Contrast that with graph 4 here. We have a main effect for factor A plus an interaction. So, going back to my definition of graphical depictions of interactions, lines that diverge, converge, or cross, these lines are crossing. This is obviously an example of an interaction. It's also an example of a main effect for factor A at low stress versus high stress. When we average across these 2 points here, the average is around 68. The average across these 2 points is about 58. 58 is significantly different from 68. And so we would conclude that there's a difference between the low and high stress conditions. What about factor B? Well, what's the average for the no drug group across level 1 and level 2 for stress? And so the average of 70 and we'll say 50 is around 60, and the average of 65 to 60 is about 62. So 60 to 62, the average between these two is not significant. No main effect for factor B, but there is a main effect for factor A. Average here, those are different. This is actually the graph that we depicted on the previous slide, showing that there was a main effect of stress, but no main effect of drug, but an interaction. The effect of drug depended on the level of stress. Continuing on with our discussion of graphical depictions of the 8 possible outcomes, we have graphs 5 through 8. Graph 5 shows a main effect for factor B plus an interaction. So here's factor A, low versus high stress, factor B, drug versus no drug. So let's isolate factor A first. The average at low, averaged across the 2 levels of drug, is 65 at the low stress. And at high stress, the average of these 2 points is also 65. So 65 and 65 at low and high stress, there is no main effect of factor A. Factor B is the drug, and so what for the no drug condition, what are the average across the 2 levels of stress, low and high? 65 and 60, that is 65 to 55, that would be an average of around 60. And 65 to 75, that would be an average of around 70. 60 is different from 70. There is a main effect of B, factor B, or drug, but no main effect of factor A. Furthermore, these lines are diverging, suggesting that there is an interaction operating here. So no main effect of factor A. There is a main effect of factor B, and the lines are diverging, indicating an interaction. Graph 6 shows a main effect for factor A and factor B plus an interaction. So factor A, the average of low and high, what's the average across these 2 groups here? Well, the average at no drug and drug at the low stress is 70. At the high stress, the average of these 2 points, 70 to 50, is 60. So 70 versus 60, that appears to be a main effect of stress, low versus high, and drug versus no drug. And so what's the average across low versus high for the no drug condition? This is 70 versus about 55, and so that would average to be about 62. The average for the drug condition, 72 to 72, that is 72 versus 62. There's a main effect going on here. So we have a main effect of stress, a main effect of drug, and these lines are diverging again, indicating an interaction. Main effects for factors A and B plus an interaction. Graph 7 shows an interaction only. So factor A again is stress, level 1, level 2. The average at low across the two drug groups here is 60 at the low stress condition. Furthermore, it is 60 at the high stress condition. No main effect of factor A. What about main effect for factor B or drug? The no drug condition at the low stress is 45. At the high stress is 70. The average is somewhere around 60. For the drug condition, it's 75 in the low stress condition, and in the high stress condition, it's 45. The average is also around 60. No main effect of drug. What about interaction? Well, absolutely. We have lines that are crossing here. There is clear evidence that the effect of drug depends on level of stress. There's no main effect of stress. There's no main effect of drug, but the effect of the drug depends on the level of the stress. Lastly, we have no effects at all. The average of factor A or stress, the average of these 2 points is 60. The average of these 2 points is 60. No main effect of stress. Low and high averages are exactly the same. For factor B or drug, no drug versus drug, the average of these 2 points, again, averaging across the levels of the other independent variable, in this case stress. This is averaged across these 2 points. Average this point to this point is 60. Average for the drug group at low and high is also 60. There is no main effect of drug. There is no main effect of stress. And these lines are absolutely parallel. In fact, they're on top of each other. There is no interaction operating in this graph either. No effects whatsoever in graph 8. So I'm going to conclude there. I encourage you to look at the graphs in the PDF handout depicting the 8 possible outcomes graphically. I will expect students to be able to look at a graph, to be able to isolate the independent variables. I will only, on the exam, I will only present it as a 2x2 factorial design that gets a little bit more complicated when you start adding more levels and certainly more independent variables. But I do want students to feel comfortable to be able to look at a graph and say, aha, I see that there's a main effect of factor A, for example, but there's no main effect for factor B, but there also does seem to be an interaction. That is important information to be able to ascertain from graphical data, and so I will expect you to be able to do that on the Module 3 exam. And with that, I'm going to conclude this video lecture, unpacking the basic elements of factorial designs, making a distinction between main effects and interactions, and also discussing the ability of students to look at graphical depictions of data and draw conclusions about main effects, interactions, main effects for either of the factors and or interactions that exist in those graphs. If you have any questions from this portion of Chapter 8 or from this video lecture, please post that question in the appropriate discussion thread, and I will, or one of your classmates will, answer it as best we can.